Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. In this video, we will talk about histogram matching, or coded histogram specification, which is an algorithm for transforming an input image to the one with a specific histogram. The outline of this lecture includes introduction about the idea of histogram matching, histogram equalization about the way to equalize the histogram of an image, that is, make the histogram become uniform distribution, matching algorithm about the matching steps of transforming the input image to the one with a specific histogram. Firstly, we define what the histogram is. For an low-level digital image, a histogram is a discrete function p of r with r equal to 0, 1 to L minus 1. P of r equal to k is the percentage of pixels with gray level equal to k, and is defined as nk over n, where nk is the number of points with gray level k, and n is the total number of points. For example, here is a 3-bit image with 8 gray levels. This picture shows its histogram, where P of r equal to 0 is 19%, and P of r equal to 1 is 25%, and so on. Given an image with histogram P of r and a target histogram Pz of z, the histogram matching is to generate a processed image so that it has a histogram as the green one approaching to the target distribution Pz of z. Accordingly, we can consider the problem of histogram matching as how to find a transformation from Pr of r to Pz of z. The idea is to take the uniform distribution as the bridge, that is, transform from Pr of r to Pz of z by a uniform distribution. Firstly, we find the function t that transforms Pr of r to uniform distribution. Then we find g function that transforms Pz of z to uniform distribution. Accordingly, the transformation from uniform distribution to Pz of z can be achieved by finding g inverse function. Finally, we can transform from Pr of r to Pz of z by the function g inverse t. Next, we talk about histogram equalization algorithm that can transform a histogram to uniform distribution. Given a histogram P of r, the histogram equalization is to design a transformation function t that can equalize Pr of r to uniform distribution. The transformation function for histogram equalization is defined as this equation, where L minus 1 is maximum intensity, and this term is cumulative distribution function. In other words, t transfers value k to L minus 1 times sum of all percentage of points with gray levels less or equal to k. For example, t transforms value 0 to L minus 1 times P of r equal to 0. T transforms value 1 to L minus 1 times P of r equal to 0 plus P of r equal to 1, and so on. Designing t in this way will transform the given histogram P of r to uniform distribution. Since the detail and the proof is beyond the scope of this video, you can refer to the video coded histogram equalization in our channel. An example of P of R is shown in this picture. According to the above discussion, the function t transforming P of R to uniform 1 is defined as this equation. It transforms 0 to 7 times 0.19 and equal to 1 after rounding. Here, 7 is the maximum intensity. Then it transfers 1 to 7 times 0.19 plus 0.25 and equal to 3 after rounding. Lastly, it transfers 7 to 7 times this term, which is equal to 1 and finally equal to 7. Here shows the t in a schematic form. Following this transformation, we can equalize the given P of R to uniform distribution, and this process is then called the histogram equalization. After introducing histogram equalization, we next talk about the detail of histogram matching. The problem of histogram matching can be formally stated as follows. Given a source histogram PR of R and the target histogram PZ of Z, the objective is to find a transformation from PR of R to PZ of Z. For further explanation and discussion, we use the examples of the source histogram and the target histogram with add labels as shown here. In general, the matching algorithm consists of 4 steps. A first step is to apply equalization algorithm to find transformation T that transforms source histogram PR of R to uniform distribution. Similarly, at step 2, it is to find transformation G that transforms target histogram PZ of Z to uniform distribution. The step 3 is to compute the inverse of G that maps uniform to Z. The final step is to form the function G inverse of T that transforms from R to Z and use it for intensity transformation. The first step is to compute a T function using histogram equalization algorithm. Since the example of source distribution PR of R is the same as the one in histogram equalization, we have T function the same as before. In addition, we show T function in a tabular form as well for further processing. At step 2, we find G function that transfers the target distribution PZ of Z to uniform according to this equation as mentioned in histogram equalization. Transform 0 to 0, transform 1 to 0, and so on. Here we show the target distribution PZ of Z, G function that transfers PZ of Z to uniform distribution, and the G function in a tabular form. Since G is a function that maps from Z to U, by definition, G inverse function thus maps from U to Z. Accordingly, we can compute the G inverse by exchanging the input and the output of G function. In digital image processing, the obtained G is a discrete function instead of continuous function, which has one-to-one mapping. Therefore, we have to deal with 2 cases when we want to compute a G inverse function. The first case is that the mapping is not unique. That is, one input value will map to multiple output values, as the red circle shows here. The strategy used here is to choose the smallest 1z for output by convention. The second case is that no mapping exists, as the green circle shows here. The way to solve this problem is to use the output of the U value that is the closest to current one. Accordingly, the G inverse maps 0 to 0, which is the smallest one, then maps 1 to 3, 2 to 4. Since there is no mapping for U equals to 3, it uses the same output of value 2, which is closest to U equal to 3. Similarly, we map both 4 and 5 to 5. Finally, we map 6 to 6 and 7 to 7. Thus, we can obtain the G inverse function. At the final step, we combine the T and the G inverse functions to transform from R to Z. The R value equal to 0 is firstly mapped to 1 through T function, and further mapped to 3 through G inverse function. Accordingly, G minus of T function maps from 0 to 3. Similarly, it maps 1 to 4, maps 2 to 5, and so on. Based on the obtained G inverse of T function, we then transform the intensity in input image to the output image. For this example, the intensity 0 is transformed to 3 and 1 to 4. After scanning all points in the input image, we can obtain the output image whose histogram approaches to the given target distribution. In this lecture, we detail the histogram matching algorithm that transforms the histogram of an input image to a specific target histogram. Thanks for your listening and have a nice day.